This is a CDC Hawk drive, and in the previous episode in this series, we got this thing fully functional. We were able to take control of the drive, we were able to send the heads out, fly them over the platters. Everything is looking great, except, well, it still doesn't work with our system. The drive is working at 100%, but the system cannot actually use this drive, which is weird because the Centurion mini computer here, which if you want to know more about, there's like 60 episodes on it on this channel. So there's a lot of information out there about this machine now. But this mini computer was actually designed to use Hawk drives. And the primary Hawk drive that we're using on the primary cabinet over there is 99% identical to this one. The only difference is how the read-write heads are constructed. Centurion normally uses a read-write head called a pre-erase head. This means that the erase coil precedes the read-write coils. That way, as the magnetic material flies by, the erase coil aligns all of the bits in the same direction, and then the write coil lays them down and flips them as they should. But this particular drive was never actually sold with a Centurion. I believe it was originally sold with a Wang mini computer, and I got it from Dave McGuire up at the Large Scale Systems Museum in Pittsburgh. If you haven't heard of the LSSM, go check it out. It's a pretty awesome place, and Dave is an awesome guy. But he so kindly let me get my hands on this, and we tried to bring it up, and it turns out that this drive uses something called straddle erase heads. This means that there are two little erase coils that straddle the read-write coil. And I had thought in the previous episode that this meant that in order to erase a sector, you would need to energize the write coil and the erase coils to essentially erase a sector, then wait a full revolution for the sector to come back around, and then you would write down new data. Now, I still believe this is 100% valid way to use this disk, but it does mean that it's going to be a lot slower when writing data down because you have to wait for 2 revolutions. And a lot of people jumped in the comments and said, I don't think that's necessarily the case. You could theoretically just write down new data over top of the old data that's on that sector. Now, there's a lot of things that could be playing into that would mean that that's not possible. Coercivity and is the internal electronics fast enough to constantly switch between the 2 coils to write down the correct data. There's a lot of things that could be going on here. And so I think legitimately both methods are viable. But if both methods are viable, how come the Centurion can't use this drive? If it's a viable method, the Centurion absolutely should be able to write something down. And so I started talking with a good friend of mine, Ken Romaine, and we have some ideas. And here he is, the man, the myth, the legend, Mr. Ken Romaine. Ken reached out to me many moons ago. God, that was like, what, 3 years ago now? Yeah. He reached out to me and said, hey, I used to work at Centurion, and he wanted to come out and help me bring this machine up. And honestly, this entire mini computer, the Hawk drives, none of it would have gotten to the point that it got to today without Ken's insane knowledge. But this mini computer company went bust in 1984, so to actually meet somebody who used to work there is pretty wild. So Ken, why don't you tell everybody what you did at Centurion?
Well, I was the first field engineer, first engineering tech, so I think I was like employee number 6 back in 1985. I spent a little over 10 years, almost 12 years there, and basically CPU 4, 5, 6, and CPU 7 days. So, you know.
So did you have any experience working with these drives?
Oh, that's how I got my job. They had a broke Hawk, and nobody could get it fixed, and I knocked on the door, and Henry said he fixed that drive, he got a job, and about an hour later the drive was fixed and I had a job, so I was employee 6.
So there you go. If there's anybody that can help me figure out what on earth is going on with this drive, it's Ken here. So Ken, when I was talking to you before on the phone, you said that you think you can potentially get this going with a straddle erase head, and you have a theory as to why. So what's that theory? What did you tell me?
Well, you know, almost 50 years ago now, mine's a little foggy, but the alignment on index to burst on a straddle erase was 18 microseconds, and on the pre-erase that we've used in the Centurion configuration is 100 microseconds. That's all based on a reference pulse of 1 bit on this alignment disk. Probably for every 1,000 Hawks built, there was 1 alignment disk made. This disk costs more than the whole hard drive cost back in the 70s. So it's a very rare thing that David's found. But that delta between 18 microseconds in relation to the index pulse, so the sector strobe, we expect to be in the middle of a data preamble or an address preamble to synchronize the read operation. And if this one reference on a straddle says 18 microseconds, the same track on a pre-erase is 100 microseconds, there's 80 microseconds of time missing. So we're going to try to find that 80 microseconds, see if we can compensate for it on the cartridge. And if we get that to work on the cartridge, then we'll have to figure out some way to do it on the fixed disk, because it has a different issue, again, with the 80 microsecond missing, but there's no mechanical adjustment on the fixed disk. If you ever see a disk pack with a black stripe on it, it's special. Talk to Dave about it. But if you imagine this is the alignment track, when you bring the head in, you do head alignment, you're moving the head in and out over this track, cylinder 146, to get your cat's eye pattern. But there's also another thing, what happens about rotational delay, and that's this missing 80 microseconds, because there's one notch on a sectoring ring in this pack that says the sector's here, and either 18 microseconds or 100 microseconds later, the head sees that pulse. That pulse is the same position no matter which head you use, pre-erase or straddle erase. So that's what we've got to compensate for. The straddle erase expects to see that pulse at 18 microseconds, pre-erase at 100, and it's the same pulse in the same position on this disk. So we have to electronically move this platter farther back 80 microseconds electronically.
And then we might be able to lay down data. It's, I don't know. It's worth a shot though. There's, I think, a lot of stuff that we can learn here. So let's pull the scope out, let's get this drive spun up, and let's try to figure something out. First things first, we got to get the drive out of the cabinet, which is no small feat. This thing weighs 135 pounds, meaning that at just 10 megabytes, that's a whopping 13.5 pounds per megabyte. With the drive safely on the table, let's get the scope hooked up to the index pin and the sector pulse pin. This is something I should have checked in the previous episode, but better late than never. Once the drive is fully up to speed, let's take a look at the scope, and yeah, that looks all right actually. That's a proper 16 sectors per revolution, but it's only the removable pack because that's what it defaults to. I need to load the heads and take control of the drive from the computer to check the fixed pack. So I'll remove the cotter pin to unlock the heads and plug the voice coil back in. And after waiting the requisite 65 seconds during power up, the heads load and everything still sounds good. So I'll hop into the memory monitor here and I'll just make sure I've got this drive selected. Then I'll do a quick RTZ to double check that we have control of the drive, and yep, chunk, that's good news. Next, I'll load in cylinder address 1000 into the disk controller register and tell it to seek to that address. And yeah, that one's looking good too. Now let's check those sector pulses again. I'll punch in F140 and set it to 00. Then let's check the scope, and yep, that's the removable, still showing 16 sectors. Then we'll punch in F140 again and set it to 01 for the fixed platter, and okay. Yeah, that's way too many sector pulses. That's like 64 pulses, and I'm supposed to have 16. Time to spin this thing down and see if we can get to the bottom of this. And the first step is to check the sector card. It has a bunch of dip switches on it for setting divisors, and sure enough, this dip switch on the top right is set wrong. Comparing it to a known good card, I've got one switch flipped in the wrong direction. I'll just grab my wave rake here and flip that to the correct position, and then go through and double check the rest of the dip switches on this board. But what did this dip switch actually do? And well, now that I've had time to kind of sit down and really dig through the manual and see what's going on, I've got the dip switch settings going on here, and the one that we had set was we had divide by 1 flip to on and divide by 4 flip to off, and those should be backwards. They should be the other way around. If we're doing a divide by 1, that means that all the 64 pulses, the 64 holes that are on the sectoring ring on the bottom, are just passing straight through, and that's why we were seeing 64 sectors. So we need to actually divide that down. So 64 divided by 4 comes out to 16, and that's how many hard sectors that the Centurion actually wants. So with that dip switch set correctly, it all seems to be working correctly again. So let's see what kind of data is coming off of this thing. In this scope shot, we can see the index pulse in yellow, and then random small bursts of data here and there in purple, which makes a bit of sense. This platter has not been low-level formatted. On the memory monitor here, I'm going to do a format write command. This just writes a new preamble, postamble, and fills the data with something. And on the scope, it looks like it successfully did that. We can see something resembling an FM encoded preamble, then a nightmare of data junk, followed by a tiny postamble. All right, let's do that same format operation again, only in different sectors. I'll increase by factors of 2 here, formatting sector 2, then sector 4. The format command is a 2-part command of sending 06, then 05 to the MMIO register F148. Back on the scope, and nothing's changed. That's not good. That means that some sectors are formatting and some aren't. All right, I think we might still have some faults on some of the boards in the drive. Let's start grabbing spare boards from the known good drive to double check. And after spinning everything back up, yeah, it looks like we're formatting the correct sectors now. I have no idea why the formatted data field looks like utter garbage, but it looks like we're getting preambles in the correct location at the very least. Let's hop back to the memory monitor here and run some tests. Let's tell it to read at address 1111 by sending 00 to F148. We get back 1070, which means a formatting error on that particular sector. Next, let's do a format of that sector by sending 06, then 05 to F148. Then we'll read that sector again by sending 00 and wait, what? 0070 means a successful read. This thing appears to be working. All right, let's try a low-level format by running the assembly program I wrote in a previous episode. I'll move the raw hex over and then I'll double check that it got into the memory correctly. Then I just need to type G0200 and it starts the program. And I'll tell it to format the fixed platter and it failed. It seems to be getting stuck in a loop, and since I'm the one that wrote the code, which I have printed out here, you would think it would be easy to figure out what's going on, but it took me like the better part of a day to work through my own code, despite the fact that I commented it to to the end of the earth and back. But I think I finally got it sorted out. With the benefit of hindsight and knowing kind of what failure it is that we're coming up against in the drive itself, the code is halting in a very interesting way. So essentially what's happening here is we start at 0 and we format sector 0 on track 0, cylinder 0, etc. And then we tell it to seek to the next sector. Now, granted, each sector doesn't actually need a seek, but to make the code simple to write, it was just increment by 1, then seek, then increment by 1, then seek. And we just do this over and over and over again. So even though we're only going to the very next sector, sector 1, we're telling it to seek. And we have all of these checks down here. We have a check that the drive is ready, check that it's on cylinder, and finally we have a check seek complete. So we're loading the drive status in and we're checking that the seek has finished, and if it hasn't, we branch back up to check seek. And this is where we're failing, because we have a failure in the drive that is preventing a bit from clearing. And I didn't put any error checking into this little tight loop to check if the drive was unhealthy. I wrote this program assuming that the drive was healthy. So we've got an unhealthy drive that is causing my program to lock up, essentially. But at the time of filming all the stuff that's happened several days ago, I still wasn't sure that it was 100% not the fault of my code. I mean, after all, I'm the one who wrote it. So let's get this thing daisy chained up with the original Hawk that's known good and try OPSIS level tools. To daisy chain them, I have to remove all the resistor packs off of one of the drives because we only need termination resistors on one. Then I need to do a lot of snaking big honkin' ribbon cables around. And finally, here we are in the operating system and it sees the drive. That's pretty excellent news. We'll try to format platter 5, which is the fixed platter, by running s.newdisk. And it thinks the platter is guarded. That means it's not seeing the right bits in track 0 sector F, I think. Let's do a .noguard on 5. And whoa. Abort 29, lost interrupt from disk. That is a new one. I've never seen that failure before. And at this point in the troubleshooting process, Ken and I were very confused because that was a new error. Everything seemed like it was working perfectly. I mean, we could go into the memory monitor and we could format a sector and read back from that sector. But it just wasn't working in the operating system. And so we turned the camera off and we just hunkered down and got to work doing a phenomenal amount of troubleshooting. And one of the things that we wanted to troubleshoot was getting some disk seek tests going on. So stored on this good hawk behind me, we have the program $?DSKT, and we're able to essentially exercise the drive from there. And we did this random seek test that seeks to random cylinders just on end, and it is absolutely wild. It shakes the drive to death nearly. But I actually pulled the camera back out for this and put it into 120 frame per second mode. So the footage that you're seeing is now going to be slowed down to 4 times slow motion. And you can tell that it actually still looks ridiculously fast. The only way you can tell that it's slow motion is by looking at the cables coming from the heads. They move in kind of a strange way, but man, this thing really books. However, fun shenanigans aside, we're kind of running out of ideas as to what the fault could be here. Finally, we're thinking it might be a data recovery problem, so let's pull the data recovery board and replace it with a known good one. Back in OPSIS, we'll do another .NoGuard5, and holy shnikes, it worked this time. It flipped the right bits. Let's go for broke and run s.newdisk on platter 5. And oh man, this is crazy exciting. Just talking about it again here. I mean, I know what's gonna happen, but oh, it's getting me so excited. I was wrong. I thought this drive could not be used with the operating system, but here we are. The operating system is formatting this drive. Unbelievable. After the format, it does a few high-speed seeks across the entire range. Then if we run a quick .sta, we can see that both platters have been formatted. And I can do a .dir and list the directory of one of the platters. This drive is fully functional, has 4 good heads in it, and apparently the operating system and the disk 1, disk 2 controller card on this thing don't care that it's straddle erase. This is insane. So first things first, in the previous episode, I was 100% wrong. I thought that the disk 1, disk 2 controller card would not play nicely with straddle erase heads because they're constructed very differently and they aren't doing pre-erase, so the bits are going to have to flip in different ways, and we were thinking there was going to be speed. I was wrong. I was completely wrong. Turns out this works. And I'll take that loss because in the end, it means that this is an epic win because it expands our ability to find new heads for these old drives. Now, a lot of people left comments, why don't I try rewinding some of the pre-erase heads? And I'm absolutely going to try to do that. That is on my list of projects that are coming up, so keep an eye out for it, but it might be a little while. But in the meantime, we have a fully functioning straddle erase drive. But what went wrong? So we had 2 big failures that were tripping us up. First of all, we had the dip switches set wrong on the sector card, and that got the sector pulses coming up correctly, but one of the sector address lines on that sector card seems to be dead because the machine is writing incorrect things into the wrong places there. So right now, currently, there is the sector address card from the mini Centurion in there, and that's why it works. But I have 2 more sector address cards. One is a spare that came out of this extra card cage that I have, and one is the one that came out of this drive, and they're both bad. So we need to fix one of those because I would like to have the sector address card that's supposed to go in the mini Centurion back in the mini Centurion. But we also had a data recovery problem. It looked like we were laying down data correctly, but it definitely wasn't coming back correctly. So the next step is to actually go to work on this card right here. This is the sector address card, and I think we can pretty easily figure out what is going wrong because so much of this card is already working. So we'll plug this card into here and we'll start probing around on the sector address lines to see if we've got one that's bad. And if we can figure out which one's bad, I can trace it down to specific ICs on here. And then hopefully we can get this sector address card fixed so the original board can go back into that drive and we can have 3 fully functioning Hawk drives in this room. So let's get to work. To figure this out, we need to do a bit of probing on the back here, but we also need to kind of understand what is going wrong. Whenever we try to write something on the bad sector board here, sometimes it writes to the correct location and sometimes it doesn't seem to write at all. So that might mean that we have a problem with our sector address. So the way that this works is the disk controller will send a cylinder address and a head select signal to the drive. The drive will seek to that specific location, select the correct head. But there's 16 sectors in that location that that head is reading. And those 16 pulses go into a counter chip that is counting up from 0 to 16 in binary. And it's sending that binary count back to the disk controller card. And when the disk controller card sees the correct binary value for the sector that it's trying to get to, it will then pull the data off of the drive. And if that sector address going back to the controller card is wrong, then that can throw the whole thing out of whack. Now there's a lot of sector address pins that we can check on here because this thing can support up to 64 hard sectors, but we really only care about sector address 0, 1, 2, and 3, the 4 that will make up 16 in binary. And we can check those pins on the I/O card right here on the back. All right, I've got the scope set up here with the purple trace on the index, so we're looking at 1 full revolution, and the yellow trace is looking at sector address 0. And because this is counting in binary, sector address 0 should be exactly half of the total number of pulses that we've got. So there's 16 pulses, we should have 8 low-level pulses here. So 1, 2, 3, 4, 5, 6, 7, 8. Sector address 0 is working perfectly. Let's check sector address 1 next. And this should be half again, so 1, 2, 3, 4. Looks like sector address 1 is working perfectly. Let's go to sector address 2, which is pin B4 here. And look at that. Okay, sector address 2 is high all the time. We don't have any pulses. We should be seeing 2 pulses going on here. So sector address 2 looks to be dead. That's not good. Let's check sector address 3. This is the last sector address that we care about. And we have 1 pulse. So sector address 3 is working correctly. So we have a good 0, 1, and 3. Sector address 2 is high all the time, so our binary count is going to be totally broken. That would explain why we're writing stuff in the wrong place. Let's pull that sector card out and see if we can figure out what's going on. Thankfully, CDC has some pretty excellent schematics, which should make troubleshooting this particular problem a lot easier. Thank you so much, BitSavers, for making these available. They're going to save my skin for sure. But we know that SA0, 1, and 3 are all good, but SA2 is bad. And that's going to be pin 5 coming out of U4 here. We know that that one's bad, so we don't need to check pin 5 here. So let's check the input coming into U4, which is pin 4. But I'm going to have to solder some flying leads onto this so that way I can test it while it's plugged into the card cage. So I should check pretty much everything all the way back to the counter IC, all the way back to here. So we'll also check U4 pin 2, and then we'll also check U10 pin 5. That should let us see the sector address pulse all along the path, and wherever we lose it is where we're losing the plot, and that could indicate which IC is bad. Okay, we're spun back up. We can see that we have our index pulse up here, and this is looking at SA0, so we know that everything is working correctly. So let's go ahead and check our 3 little flying leads up here and see what we can see. I forgot what order I put these in, but we have the pulse there. We have the pulse there. And we have the pulse there. So we have the pulse on all 3 leads here getting properly amplified and output. So that means that we're losing it after the last IC or within the last IC, because it looks like we have the proper input to that IC. Okay, that's interesting. It looks like we might have a bad driver chip on the end there. Okay, the IC for sector address 6 has been placed in the place for sector address 2. So let's go ahead and just check all the sector addresses again, see if we've fixed the problem or if we've made it worse. This is sector address 0. That's looking good. So we'll switch over here to sector address 1. That one's still looking good. That's good news. Here's the one that was broken before. And yeah, there we go. We got it back. That's sector address 2. And finally, sector address 3. It looks like we are working at 100% on our sector card now. Let's plug this back into the computer and hopefully it all works. Here we are back into the OS. Let's do a .sta, see if it sees the drives. Yeah, that's a good sign. LSSM0, LSSM1. Let's do a directory on 5 here. Yeah, let's copy something to it. Let's do a directory 1 to find a nice small file that we can copy over here. And we'll copy ZUB here. This is actually quite a big file, so we're going to stress test it a bit. That is 6 tracks. So we'll do an s.copy ZUB from 1 to ZUB on 5. We'll hit enter. There is no in library, there's no out library, and it's going to go to work. Okay. Disk fail. What? So we had a failure. Wow, okay, that's interesting. 1070 is a format error, so that means that it didn't see the correct bits. Now, the sector card that we put in there could be adjusted slightly differently than the one that we were doing initially. So let's just new disk that one and see what happens here. Wow, all right, new disk failed. Boy, we've got some interesting problems going on here. 8070, I don't know which one that one is offhand. So we still definitely have something wrong with the sector card in here. No matter what software I throw at this, neither the fixed platter nor the removable platter ever seem to work. We always either get a format error, which means it didn't see the right preamble, a sector address error, which means it saw the right preamble but not the right sector address, or a timeout error, which means it never saw a sector address through 2 rotations of the disk. So there's definitely something still going on related to the sector address, it seems, even though on the scope I can clearly see that the sector address looks correct. And if I pull this sector card out and put the known good one in, it all springs to life. We can use it within the operating system as if though it were always meant to be. So, man, I don't know what's going on. The way that the sector card is built is that the fixed platter and the removable platter are kind of completely separated circuits all unto themselves until the very last section where they get multiplexed together, and depending on which one you have selected, and outputs that to the card here. So maybe we still have a problem around that multiplexer area, even though it all seems to look okay on the scope. This is going to require a lot more finesse than I may be able to pull, but I'm going to take another swing at it. Hopefully we can figure it out. Several hours later, and we're in a pretty good spot. If I do a .dir4 here, you can see the directory listing of the removable pack is fully visible. The same goes for the fixed platter on here. I can write files to it. This drive is fully 100% usable in the operating system, and it's doing it without the known good sector card that came out of the mini Centurion. But it's also doing it without the sector card that originally came in it. That's this card here. I could not figure out the fault. Everything on the scope looked good, but the machine was unhappy with whatever this sector card was doing. But here we are with the drive fully working, so maybe I don't need to troubleshoot that one. And that's because I'm using the sector card that came out of my spare card cage here. Initially, whenever I put that sector card in, I had obviously tried that before because swapping cards is always easier than troubleshooting weird marginal ICs. But whenever I would turn the drive on, it would spin up, kick off the fault light, and spin down. I could not figure out what was going on. So I pulled it out and I started checking the dip switches. I thought maybe a dip switch had bad connection. And a couple of the dip switches showed about 3 or 4 ohms across them when they should have been essentially a dead short, 0.1 ohms or something. So I toggled them back and forth until they were making good connection. I put it in and that still didn't fix it. I was super confused. So I put all of the termination resistors back in it because I wanted to see if it was getting the appropriate signals, the index and sector signals, out to the I/O card. I spun it up and it worked. I don't know what changed between when it didn't work and how it works, but I power cycled this 3 or 4 times. I've written stuff to it, so that sector card is fully working, and that sector card is going to stay in this drive because that means that we now have 3 fully functional drives. Well, almost 3 fully functional drives. In the process of this, I have slightly injured the mini Centurion drive, but it's nothing that we can't overcome. And I'll explain exactly what happened with that after I clean up this kind of discordant nightmare that I have going on here, because this is kind of precarious. So I'm gonna get this back into that cabinet, clean up all the cabling, and then I'll come back to you guys and explain what happened to the mini Centurion, and maybe we can get it fixed so we can have all 3 drives fully functioning in this room. The wide angle of the camera can sometimes make the room look a lot bigger than it actually is. I mean, don't get me wrong, it's not small. I've got 275 square feet here, or 25 square meters, but the layout is pretty narrow at 25 feet by 11 feet. Also, I like every system to be equally accessible, which means I have to be pretty smart about the layout, and I have to be ultra vigilant on keeping the room clean. I often take breaks like this in the middle of filming just to clean the place up and get the room back to a known good state. But it also means I use all sorts of unorthodox places as storage, like the bottom of the second Centurion cabinet here. This was a storage place for random Hawk parts, but with a real working Hawk going in, it's time to clean it out. Now, hoisting the Hawk itself back in should be a 2-person job, but it's really only about 135 pounds, and that's definitely heavy, but not beyond being a 1-person job. And with the Hawk back in place, now comes the fun job of connecting it up to the main computer. I have to pull both cabinets out so I can get access to the back as well as the inside. On the inside, there is a lot of cable management that I need to do, especially with there already being 1 Hawk, 1 Finch, and 1 floppy all contending for space in here. Then the cables come out the opening in the back, flip a 180, and head into the other cabinet. And all the extra length will hang out in the bottom of the second cabinet. Then it's just a matter of tidying the whole thing up and sliding the cabinets back into place. And finally, we're here at the mini Centurion. Now, why am I messing with this one while we've been working on the other Centurion all day? Well, this is the known good drive that I've been pulling boards out of to test in that other drive. But now that that other drive is up and going, I put all of the boards back in this one, spun it up to make sure that it was still healthy, and it wasn't. I could boot into the operating system, but only on the removable pack. The fixed platter was totally unreadable. I went into the memory monitor at the lowest level and started trying to do format writes and read backs on the fixed platter, and weirdly the Hawk was throwing faults. And that's when it realized that I probably had something hooked up wrong, and sure enough, I had gotten the plugs that go into the read-write erase card for the heads. On the fixed platter, I'd gotten those off by a couple of pins, and well, that blitzed a couple of sectors on the fixed platter. And so once I got those in the right place, I was able to kind of get back into the operating system, and you can see here that the fixed platter is recognizable now, but there's no files in it because I had destroyed a couple of very important sectors while we were doing that. But I didn't just destroy the sector, I destroyed the preamble and the postamble. So it can't find any of the syncing data that it needs to have. Now, normally you would just do a low-level format on this platter and call it good, but this version of the operating system has had the low-level formatting tool stripped out of it, which is awful. So I had to write a new low-level formatting tool. I did that in a previous episode because we've had this problem before. So all I need to do today is to plug my laptop back into it, get into the memory monitor, load up the low-level formatting tool that I wrote, run it again, and then we should be totally fine, hopefully. Thankfully, we can still boot off the removable platter, and a memory monitor is stored in the question mark folder. I can just boot into that and load my format program directly into memory. The program has to live at address 0200 hex, and the glory of Terraterm is that I can just hit Alt-V and it pastes the hex code straight in for me. And once it's all in, I just type G0200, telling it to jump to address 0200 hex and start executing the code there. My program asks me which platter, and then it just gets to work. And unlike earlier, it seems to be working perfectly this time. It takes about 7 or 8 minutes to fully low level the 5 megabyte platter. Once it gets to the end though, it will throw some errors. That's what all of these X's are, but that's not a problem. I accidentally wrote the program to try to format a couple cylinders beyond the actual disk end, so it gets a little upset about that. Back in the OS here, it sees the disk, and let's try running the copy program again. And it just hangs right here. That's not good. I feel like I'm forgetting something. Reverting back to my laptop, I pulled up my old episode when I last did this, and sure enough, I forgot a few vital steps. Thankfully, I had this episode for reference. But now that the platter has been low-level formatted, we need to run a .clr to clear it out and get it ready for data. Then we follow that up with a s.loader, which copies the initial program loader over to track 0. I suppose this is a bit like copying the sys files over on a DOS drive. Then finally, we can just run the dump program. It'll ask for source disk, target disk, and a few other questions I don't really care about. Then it's off to the races, actually copying stuff over. Now on the occasion, it looks like we're getting I/O errors reading the removable pack, and I think my removable alignment may be slightly out of whack, or perhaps something a little more sinister is going on. I have an idea as to what that might be, but I'm going to talk about that here in a minute. Ultimately though, the copy finishes up and the disk is fully readable, and I was even able to boot off of it no problems. That is excellent news. And after feeling like a bit of a dum-dum for a while there, check it out. The whole room is up and going. The mini Centurion is fully spun up and in the operating system with a working Hawk drive. And if we come over to this side, the printer is fully functioning, the primary Hawk drive is fully functioning, and the secondary Hawk drive is fully functioning with working data terminals on top. And that little EDS PC is chugging right along. Everything is working perfectly, except they're not all working perfectly. Both the mini Centurion and the straddle erase Hawk over here still have problems. The mini Centurion is getting increasingly difficult to boot once the drive has been on and heat soaked for a good while. And I'm pretty sure this is a failing servo control PCB that sits on top of the voice coil. The previous PCB that was in that drive failed in exactly the same ways. And so we'll dive into that in an upcoming episode. The straddle erase Hawk over here last night was working perfectly, and then this morning when I powered it on, couldn't read the fixed platter anymore. Could read the removable, could write files to it, but the fixed platter was totally inaccessible. It was just giving us errors. I even tried to do an s.newdisk on it, and that errored out. Finally, I was able to battle through it by doing a manual dot format to re-low level the drive, and then doing an s.newdisk to put all of the appropriate initial program loader and stuff on it. And so now, in this current state, the last time it was on at least, every drive connected up to this computer is currently functioning with the exception of the Phoenix. But I think this straddle erase drive is highlighting a problem of using the straddle erase heads with this Disk 1, Disk 2 controller card. And this controller card was never meant to use straddle erase. And I think the physical construction of the head is what's causing our flakiness. The read-write coil on the straddle erase is located in a different position than the read-write coil on the pre-erase. That means that the burst to index timing is going to be about 20 microseconds for the straddle erase and about 100 microseconds for the pre-erase. And I think that 80 microsecond difference is pushing the disk controller card right to the limit of its timing tolerances. So we might possibly be able to physically modify the transducer pickup location for both the fixed and removable to get that burst to index timing a little closer to 100 microseconds and make the disk controller cards a little happier. But in order to do that, we're going to have to use the customer engineering alignment pack because it has the burst to index pulse on it. And I'm a little nervous about using that one. As Mr. Romaine said, those packs cost as much as an entire drive, and they are very rare. Centurion built thousands of systems, and they only had 2 packs total. That's how rare these packs were, even back in the day. So I'm not going to try and fly that pack in this drive by myself. I'm gonna wait until Mr. Romaine gets a chance to come back on down. So Ken, if you're watching, I want to thank you so much for hanging out with me today, and I absolutely cannot wait for you to come back down and help me get this drive fully dialed in, because we got to do the burst to index timing and we have to do a full head alignment. So we're going to put that customer engineering pack to proper use. I also want to thank everybody who left comments in the previous episode. I was 100% wrong in my understanding of straddle erase versus pre-erase, and you guys left such amazing comments, and that inspired me to take another look at the drive. And the result of me being wrong and you guys being right is that I have another functioning drive in the room, so I will absolutely take that loss. So thank you guys so much for the amazing comments in the previous episode. And finally, I want to thank Dave McGuire for letting me experiment with this drive. We still have so much more that I want to experiment with. The straddle erase versus pre-erase conundrum is very interesting, and straddle erase heads are far more common than pre-erase heads. So that opens up an entire avenue for keeping these drives going on a multitude of systems. So what an excellent opportunity. So if you guys haven't heard of the Large Scale Systems Museum up in Pittsburgh, definitely go check it out, because Dave McGuire is an absolute legend and he's got a lot of really awesome stuff up there. So I want to thank you all so much for watching, and I hope to see you in the next episode.